Okay, so I'm going to talk about active learning for level cell estimation of black box functions. And I'm going to give 2 cents about what the algorithm, what the logic of the algorithm is like. But this tutorial is more about how to use the package um, that we implemented, that we constructed to implement this type of algorithms. So this is work done by my colleagues, Lucas, Gilles, Patrick, and Kyle, and also supported by several funding agencies. One of them is IRIS-HEP, who is also sponsoring this edition of PyHEP. Okay, so what is the motivation for Excursion? Our motivation is based on this plot. This is the typical exclusion plot, the end step of a high energy physics experimental analysis. And it's the plot that will conclude which areas of the parameter space of a new physics theory are excluded versus which ones are not. It's very expensive to produce because evaluating each of these points takes days or even weeks. So that's why we want to use our computational time smartly, and we want to query this simulator, these black box functions, which I will explain more about it later, um, as few times as possible. So the idea is that instead of using a regular grid, we just evaluate at the points that are important around the contour, and some more exploration. This has the advantage, and this is what is implemented in Excursion. This has the advantage that we can control the granularity of the estimation of the contour of the level set, because we can have a finer grid than with the current approach, and we use active learning and Gaussian processes with GPyTorch support in this library to make this possible. Okay, so that was the real world motivation. And here I have an image of a 3D function and in red, and there's a threshold in blue. And then the contours that this threshold makes in the function are above. So we are interested in finding these silhouettes, the level sets. And imagine in the high energy physics example that this surface is a CLS surface or p-value surface. And um, the domain is the parameter space of a new physics theory. So we are interested in finding what is the border that will separate between excluded parameter space and non-excluded parameter space. And also, by not evaluating the whole grid, we can also scale up in more dimension than just 2, because we are not evaluating the whole grid. This is the setting, and here we have a more formal description of the problem. We basically will have a black box function, and that is a scalar, and we want to find the set where the function takes a certain value. Okay. And because querying a real black box function is very expensive and we wouldn't be able to do it in a tutorial, we have generated some fake black box functions, and that's what we will use here today. The method consists on starting with an initialization data set, and then we train a Gaussian process over this initialization. And we use the Gaussian process as a surrogate model to interpolate between the samples of the true function that we have. Then we will calculate an acquisition function for all of the domain, which is very cheap. And this acquisition function is the same as how worth it is to evaluate that point through the expensive pipeline. So the one that has the maximum accuracy, the maximum acquisition function will be the one that we select. Okay, if you haven't fully understood the method, that's okay, because we were going to see it along with the code. This might remind you of Bayesian optimization, but our problem is a little bit more difficult because we are interested in finding curves and not just points. And these curves could be they could be non-connexed, for instance. We have inspired our library in other libraries that 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 exist for Bayesian optimization, which are Scikit Optimize and PyTorch. We're actually working on a PyTorch implementation. And we are also using GPyTorch, which has fast state-of-the-art posterior techniques. It's based on Torch. Okay, so let's get started. We are going to use, we have two tracks in here, the casual user and the advanced user. And what is a black box function? Does it keep track of something? In the Slido, black box functions simply mean that we don't have a formula for the function. It means that it's, for instance, the outcome of a simulation. You query a simulation with a certain set of parameters and you obtain numbers, and you don't know, you don't have an f of x equals a formula. That's what black box function means. So we are going to load a predefined test case in 1D out of the box. And this is the test case that we are going to consider. The dashed line is the true function. The gray line is the threshold. And we want to find the red stars, the points where the threshold meets the function. But without knowing where this dotted function is a priori. Okay. Now, once we have loaded a test case, we need to specify the Gaussian process. So if you're not familiar with Gaussian processes, well, it's okay. Just for now, know that depending on our different choices that we make about the Gaussian process, we will have different behaviors. So you need to make some choice. But if you're a casual user, don't worry about it, because we have out of the box setting for you, several of them, and in the form of a YAML file. So here we have a YAML file that I'm loading. This algorithm specs, oops, sorry. Let me show you. That has the example that we're going to run, how many initializations you want to start with, the updates, and then all of the settings for the Gaussian process, that you don't have to worry about it. And after that, I will explain what the advanced users should do. Okay, so we have loaded the specifications, and now our package is agnostic, is device agnostic, because we often need to use a GPU. We are going to initialize a GP, and this is going to initialize a GP with the options that we have loaded here. Okay, and we are going to plot this initialization. This is random, so we can run it as many times as we want, and we get different. Okay, so in here, the blue lines and the blue shadows refer to the Gaussian process, which is going to be our estimation of the true function. And we have started with two initializations. And now we would like to start running the method that I have described before, the acquisition function and so on, to try, to try to find the level set. Okay, this is for the advanced user, so that's why it's in a string. The two initializations define the prior. No, the two initializations are giving you a posterior, are giving you something to start with, instead of starting out of nothing. So the advanced user should build a class like this one, which is the GP model. And this is in the same way that GPyTorch does it. And the advanced user should specify a mean and covariance and a forward one, and a forward mode, which is always takes this shape, as long as you have specified the mean and the covariance. And then the advanced user should also initialize the likelihood that they want. And I have put links above to the GPyTorch documentation, where you can see how many likelihoods you can initialize. Then you should initialize the model with training data. Train the model manually, because again, you're an advanced user, so you'd want to have full control of the moving ingredients of this algorithm, and then you would initialize the estimator, and we are in the same page now with respect to the casual user. Okay, this is just for reference, so don't worry if you are overwhelmed. Okay, we are initializing our estimator, and this estimator is going to keep track of what is the next point that we are selecting in order to find the level set. And the several methods that it has go around this, the logic of this algorithm. It's going to update posteriors, etc. You will see now. Okay, now we're going to start the active learning loop, now that we have everything loaded. And this is just for saving the plots and the diagnostic files that will get along, which are quite a bit. We're going to run this this loop. Okay, I'm going to run it first because it will take a while. And after that, and meanwhile, I will explain what it does. So here, I want to iterate this algorithm, the active learning algorithm, a number of times. Estimator step finds the next point that you need to evaluate to in order to find the next point that you need to evaluate in order to find the level set faster. This step is plotting the update. So the Gaussian process with this new data point updated. And after that, okay, update the posterior, and we get diagnostics, and at the end we print. Okay, so for instance, in here, you can see that the first iteration selected the point 0.49, the second one, the 0.29, etc., etc., etc. And then we are going to visualize this better with a widget. This is the performance. Accuracy 1 means it has founded the level set. You can play with that later. And here is the widget. So we see that this is the acquisition function in orange. So this is the maximum one. So this is the point that we should evaluate next. And then the iteration, it does exactly that. It goes to that point and evaluates. And then everything gets updated. And we do it over and over. It's going to find more points. And at the end, it has basically founded the level set that we wanted. And as a consequence, it has also modeled very well the function, but this is not always the case. And now the acquisition function is just 0 because there's no uncertainty anywhere, and it will just start picking points in order. Okay, let's do a tweak to this first example. We're going to add noise. What happens if our black box function if our black box function is a noisy observation? If we have instrumental noise, for instance, well, we would have to add this epsilon, which in this case for the tutorial is going to be a Gaussian, a normalized Gaussian. And I'm going to repeat the exact same code that I posted before, but a bit more compact because we have seen how it works. You see that this time with noise, the evaluations are not exactly in the black box function. It's in another one. It's a bit off because there's instrumental error. We're going to run the active learning loop. And this might take a while. You can see here, this is my local computer, my local environment with the virtual environment, like we saw in the talk before mine. And here there are many files that are generated by just running these loops. Like you can keep track of all of the images in between, diagnostics, etc. So you're going to see this number increasing. Okay, for a noisy black box function, this is going to take a while more than before because the noise prevents from making a good estimation of the level set with few iterations. So we are going to wait a little bit and I'm going to answer questions in Slido. What is the prior in that case? Okay, so the prior, what I mean by prior is a prior over the space of functions, which is what a Gaussian process is. And a Gaussian process, you need to make some choices. You need to make the choice of a kernel and the choice of a mean. The mean typically is put at 0. And that's not like something that you have to care about much, but you have to care about the kernel. And there are different types of kernels that you can use. And that's what I mean by prior. These choices that you make about the surrogate model before the data comes in. All right. Let's see. Because this is a bit of a computationally intensive tutorial, would it be okay if I take longer, but I go and ask questions on the go while this is running?
Oh yeah, please do.
Okay, so there's another question in Slido that says GP is a prior, not a kernel. Okay, a GP, yes, a GP is a prior over the space of functions, and it has a kernel. It's a GP is not the same as a kernel. It's one of the components of a GP. This is taking a bit long.
It could help if, so for answering questions, it could help if you move the tab onto what you share so that we can read the question as you're
Sorry. This one? Thank you.
Mm-hmm.
Perfect. Now it's better to visualize this with a widget. So let's see what the iterations were doing. And the same, we have the acquisition function here. So it's going to take as next point the maximum of the acquisition function. And at the end, basically what we want to see is that this took many more iterations because the noise makes it very difficult to get the level set correct. But what I want you to appreciate from this picture is that all of these gray lines are the evaluations to the expensive black box function, which in our case is just generated data. And the algorithm is concentrating them along the points that really contain the levels that we're trying to find. And it's not querying the function at the points that there is no level set. So in here, 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 and here. And because of the noise, we're really never going to get it a pinpoint estimation. Okay, so this would still be faster than evaluating with this level of coarseness, but along the 1D grid. This is the end of the 1D tutorial, and with this, I'm going to show an example of a 2D tutorial. So we also support multiple functions. So we want to estimate the level sets of multiple functions, but at the same time, with the same queries. And this is what you have here. They look very similar because for convergence purposes, I made them similar so that we don't stay until tomorrow here. But they are different functions. The one is slightly scaled up. And they also have different level sets. So we want to make the same evaluations. We want to query the same X and Y points. You see that the red dots are always in the same. Let me put it. Okay, the red dots are always in the same position in both of them. And here you have the acquisition function. So in here, this is basically the more purple an area is, the more worth it is to evaluate at that point in order to find the level set of this and this function. This is a GIF that I have made with a loop similar to the ones that we had before, but we are also going to run a 2D example here with batches. So by batches, I'm going to start running this. By batches, what I mean is that so far we have only evaluated one point at a time, one red dot at a time, but it would be faster if we could evaluate a batch of points at a time and then parallelize each of those points in the case that we are, for instance, querying a simulator at CERN. And the structure of this example is exactly the same as the ones before. I'm evaluating this active learning loop, and then we will see the result in a widget. And sorry, I don't have any pre-evaluated images, so we'll have to wait to see. To see the results of the batches. I'm running this on a CPU. So now you see why is it important to have a device agnostic package if you're based on if you're going to be based on Torch, because quite easily you're going to need a GPU. See that the number of just by running these toy examples, the number of files it's quite big, because we want to keep this is expensive computation. So once we run them, we don't want to lose the information. I want it to be stored somewhere that I can check it after. That's why we made it verbose. One of the things that you can check is, for instance, the confusion matrix along the iterations. This is the confusion matrix from classification. So if we classify points below or above the threshold, and if we incorrectly classify with our estimation, we incorrectly classify some of the points, then we will have a confusion matrix, like in the same case that we will have a confusion matrix from classifying cats and dogs, but interchange cats and dogs with above and below the threshold. This is one of the other outputs from the package. And please ask your questions in Slido so I can answer them while we wait.
And just as a reminder, you have 5 minutes left in this talk.
Okay, thank you.
But it's true, I don't see any questions on Slido right now. So, but now is the great time to ask them, everybody.
Yeah.
While stuff is compiling or running, is always a good time to sneak in.
Okay, done. So we are going to visualize it in a widget, which is going to be better. Oops, it's a bit small. It's a bit too small. Well, there are 3 dots at a time instead of 1. And then let's see if the solid line matches the dashed line at the end. And it does. And it does it, if you remember the other one, it does it faster at the 12th iteration, because we are taking 3 points at each time and not only 1. So it will converge faster. Now I have a 4D example here, which I'm not going to evaluate. I have pre-evaluated it, but it's in Binder, so if you have the patience, you can do it. And in this, for the example, our true function is going to be a paraboloid, and we want to find the level set at t equals 1. So when this is all 1, and this corresponds to a 3 sphere with radii 1. So if we do the same thing, the same loop, we should find this 3 sphere with radii 1. And the way I'm going to show you is that, okay, this is evaluated. And at the end, I plotted a histogram with the norm of the selected points. So the threshold is at norm exactly 1, because it's the 3D sphere. And we have no way to visualize this as the way that we've done before. So I thought that this histogram would be nice. And this is the norm of the selected points, the points selected by the algorithm. And you see that there's a lot of concentration around 1, which is good because we want the algorithm to not waste time looking around the space, but to concentrate around the contour that we want to find. And then it does some exploration below and above, which is also good. Okay, further work here. We are working with an Irish Head fellow on improving the code, and we are going to develop multi-resolution support in the near future because of the type of research that we are doing with the exotics group at Atlas. And we're also very interested in including the possibility of querying a black box function that is external to the code in the similar way that we've seen in some other PyHEP talks here. And for instance, high energy physics simulators. That's it. Thank you for having me, and I will answer some of the Slido questions very quick. Okay, F-score of this algorithm. F-score of this algorithm, I'm not sure what this means. Can you remind me again, why do we want to have the levels, not extrema? Oh yeah, we want to have levels, not extrema, because we are motivated by high energy physics examples. And in high energy physics, we want to find the levels at the contour set at a given confidence level, so that we have an exclusion area and versus a non-excluded area for the parameter space. What kind of Bayesian optimization is using parallelization when sampling points to evaluate? How are the points chosen with acquisition function? So this is a bit, so on one hand, you have Bayesian optimization, and on another hand, what you could do if you are getting batches, using batches of points, is to parallelize those batches, and then wait for the results of these batches into your cluster, and then feed them again to the algorithm and update and start again. So it's not a kind of Bayesian optimization that uses parallelization. It's two separate things that you can combine together. And for the F-score of this algorithm, I'm happy to respond this on Slack because maybe now I don't remember what an F-score is. And I'm happy to answer that there.